All right, greetings to everyone in 510A. So this is going to be the format for the rest of the semester. I'm going to do video accompanying PDFs of lectures. So just want to take a small step back to what we talked about on Wednesday, which was the following lemma that we'll need to prove Lucen's theorem. And this is a very special case of something called Tietze's theorem. And if you're curious, you can Google that. So let's say F is not empty and closed, and little f is continuous on big F. Then there exists a continuous extension of little f that's defined on all of the real lines. So in other words, there exists a G that maps R to R that's continuous where G equals F on big F. Okay, so what's the proof? Well, so on big F, G has to be little f because G restricted to big F is little f. It's an extension. So define G to be little f on big F. Okay. And big F is closed, so its complement is open. So write the complement as the disjoint union of open intervals. Okay. So I'm going to assume that simultaneously AK is not minus infinity and BK is not plus infinity. In that case, F complement is the real line, which means F is empty, okay? Which we're assuming it's not. Okay, so that means we have three cases for looking at these little intervals. And I should mention, because this is a just disjoint union, if I define G on each of these open intervals, then G will be well-defined on F complement. And because it's defined to be little f on big F, it'll be well-defined on all of the real line. Okay. So depending on which case we're in, let's look at the first case. If AK is minus infinity, then I'm going to basically let G be the following line. So it's basically the line emanating from BK, f of BK with slope 1. Okay. So the picture is just exactly what I said. G is just the line emanating from BK, f of BK, slope 1. Okay. Plug in BK here, we get f of BK. The second case is when the right endpoint is infinity. That's basically the same thing. It's the defining G to be the line emanating from AK, f of AK with slope 1. Okay, so the picture is as follows. Right. And if both the endpoints AK and BK are finite, then just define G to be the secant line. Okay. So hopefully you remember that formula from Calc 1. If not, here's the secant line. And the picture is as follows. Here's AK, BK, both are finite. G of x on the open interval AK to BK is just this secant line. And you can check, you plug in AK, obviously get f of AK, plug in BK, BK minus AK cancels BK minus AK, f of BK minus f of AK plus f of AK. So G of AK is this left endpoint. G of BK is this right endpoint. So this is the secant line. Okay, so I claim that G, defined in this way, is continuous on R. Right? So let's just say x0 is an R, and let's get rid of the very easy case, which is x0 is an F complement. In that case, F complement is disjoint union of these intervals. So let's say x0 is in one of these intervals. Right? But this is an open interval, so in a neighborhood of x0, G is a line in either of these three cases that we talked about before. Okay. So G is absolutely trivially continuous at x0. Again, in a neighborhood of x0, we're still in AK to BK because it's an open interval, and G is a line on AK to BK, so G is continuous at x0. Okay, so let's look at the not so easy case where x0 is an f. And the easiest thing to do is assume G is discontinuous at x0. So 511, basic analysis, it's equivalent to saying that we can pick a sequence of real numbers. G is defined on R. And we can pick an epsilon 0 bigger than 0, where xk converges to x0, but this quantity here is strictly bigger than epsilon 0. Right? If you don't remember this equivalency of continuity, then yeah, it's just easy to try and prove it yourself. And we're going to use this, so let's call this star. We're going to use this quite a bit. So, okay. Well, if eventually all the xk's are in F, then this is a contradiction. Because that's saying, well, G is not continuous on F. And we know G is continuous on F because G is little f on big F. And we assume little f is continuous on big F. Okay? So what this means is that we can assume there's infinitely many of the xk's that are in F complement. Okay? And what we're going to do, actually, is we're going to prove that this is false for a subsequence of the xk's to avoid, and we're going to actually take subsequences of subsequences of subsequences. So to avoid a nightmare notation situation, we're just going to use the terminology that other books and papers use, that we're going to pass to a subsequence if necessary. Okay? Basically what that means is we're just going to take subsequence of subsequences of subsequences, but stick to the original notation for the sequence, to make notation situation manageable. Okay. And I should mention, certainly if we can find a subsequence where this is false, then it's a contradiction. Sorry. Okay, so right, if eventually all these are in F, we're done. So assume infinitely many of the xk's are in F complement, so passing to a subsequence if necessary, we can assume that all of the xk's are in FC. In other words, we're really kind of taking a subsequence, we're just don't want to use subsequence notation. So assume that this all of these are in F complement. Okay, further, by the monotone convergence theorem, because this is certainly bounded, you can assume that the sequence is monotone. We will assume that this is increasing. Homework is you assume the case when this is decreasing. Okay. And again, we're taking a further subsequence, but we're still going to use this notation because we don't want to use subsequence notation. It's a pain in the ass, and it's a nightmare if we had to do that. Okay, so in particular, because this is increasing and it converges to x0, we know xk is less than or equal to x0, and, well, actually xk is less than x0. Xk cannot be x0. We're assuming xk is an F complement, but x0 is assumed to be an f. Okay. So if you go back, we're assuming x0 is an f. This is a case where, okay, so they can't be equal. Okay, so xk, each of the xk's are an f complement. So pick an AK, BK, where xk is in that open interval. Okay. So xk is strictly between AK and BK. I claim, this is not so hard to prove, that the BK's converge to x0. Okay. So to do this, let's assume x0 is less than bk and get a contradiction. So if x0 is less than bk, then ak is less than xk, just from here. xk is less than x0 from here. And we're assuming x0 is less than bk. And that's a contradiction because, well, clearly this interval here is a subset of f complement. F complement is the union of all these intervals. And this is saying x0 is in this interval here. It's between ak and bk. So then x0 is an f complement. Again, we're in the case x0 is in f. So this is impossible. So what that means is simply that bk is less than or equal to x0. Okay, so bk is less than or equal to x0, but xk is less than bk, of course, from this here. So, right, so the squeeze theorem tells me that bk has to converge to x0. Because xk, we picked the xk's to converge to x0. So bk sandwiched between something converging to x0 and x0. Okay, so same kind of arguments, we're going to find a further subsequence where the AKs, a further subsequence of AK where that subsequence converges to x0. So again, we're going to use the same notation. We're not going to use subsequence notation. There's really no need to. Okay. So how do we prove that? Well, let's get something out of the way. First, if n of the AKs is minus infinity, then I claim that an can't be minus infinity for n bigger than k. Because if it is, well, this is minus infinity, this is minus infinity. So obviously the intersection here is not empty. And we're writing f complement as the disjoint union of these intervals. Okay. So in other words, if ak is ever minus infinity, then, well, going further, just letting n be bigger than k, we're not going to ever have minus infinity for the ans. So we can just, if it is ever infinity, minus infinity rather, for an ak, just throw it away and look at the rest of them. They're not minus infinity. Okay. So we're going to assume ak is not minus infinity. We're going to assume it's a real number. So by homework 1, I believe it's homework 1, either that or homework 2, we proved that ak plus 1 is not in ak to bk. It's not in any of these intervals, particularly it's not in ak to bk. So either that means, well, it's bigger or equal to the right endpoint, or it's less than or equal to left endpoint. And further, I can say, if it's less than or equal to the left endpoint, if ak plus 1 is less than or equal to ak, then in fact it has to be strict inequality, because if they're equal, then ak to bk, ak plus 1 to bk plus 1 are obviously not disjoint. If you have two intervals where the left endpoints are the same, they're obviously not disjoint intervals. So ak plus 1 equals ak is impossible. So let's assume this is true, B prime, for infinitely many k. One of these has to be true for infinitely many k because one of these is true for all k. Okay, so for these k, we have bk is less than or equal to ak plus 1 from right here. That's the case we are in. AK plus 1 is actually strictly less than BK plus 1. So by the squeeze theorem, well, we proved that BK converges to x0. BK plus 1 converges to x0. So that means for all these k's, we can form a subsequence where by the squeeze theorem, that subsequence converges to x0. Okay, so that takes care of this case here. Now in this case, if this is true for infinitely many k, then for these k, we're going to assume this is true and get a contradiction. So if this is true, then AK is less than BK plus 1, and B double prime is assuming AK plus 1 is less than AK. So we have AK plus 1 is less than AK, AK is less than BK plus 1. So AK is in the open interval, AK plus 1, BK plus 1. Okay. Again, that's impossible by homework 1. Okay, so that means BK plus 1 is less than or equal to AK. Okay, so this is false, so BK plus 1 is less than or equal to AK. And AK is less than BK. It's obvious because it's an interval, open interval. Okay. So again, if this is true for infinitely many k, then since BK plus 1 converges to x0, BK converges to x0, we can find a subsequence from these infinitely many k's where the subsequence for AK converges to x0 by the squeeze theorem. So again, we're not going to use subsequence notation, so we're just going to assume the AK converges to x0. Passing to a subsequence, if necessary, we can assume the AKs converge to x0. So in either case, we can find a subsequence of the AKs converging to x0. All right, so we're almost finally done. So the next thing I claim is that, in fact, g of xk converges to g of x0. Okay, why is this true? And of course, this right here is going to be a contradiction. To this here. And again, remember, we're really finding a subsequence that contradicts this. So let's go back to where we were. Okay, so x0 is an f, ak is an f, and bk is an f. Again, remember, f complement is the disjoint union of these intervals. Okay. And the homework was that AK and BK are not in any of these intervals. So, right, so they're not in any of these intervals, so they're not an F complement, so they're going to be an F. Okay, so in this case, because x0 is an F, g of x0 is equal to f of x0, g is F on big F. Okay. And because AK converges to x0, we have, by continuity on big F that f of x0 is this limit here. And the same thing, we proved that the BKs converge to x0. Since the BKs are in F, we have by continuity that f of x0 is the limit as k goes to infinity of f of bk. Okay, so, well, right, so we're assuming minus infinity is not AK. AK is less than BK. BK is actually less than or equal to x0, so it's not minus infinity. So what does this mean? This means that on the interval AK to BK, we're in our case 2, which was that g of x is the secant line. Okay. So this means that g of xk is between f of ak and f of bk if f of ak is less than or equal to f of bk. And that's just from the picture here. So the picture in this case is f of ak is less than or equal to f of bk. So xk is somewhere here. G is this line segment. So this is where g of xk is going to be. Okay. And it is possible that f of ak is equal to f of bk, in which case it's just flat line. So that's why it could be equal to one of these. But and certainly between f of ak and f of bk. And, well, if f of ak is bigger or equal to f of bk, then basically the same thing, g of xk is between these two. It's just f of ak is the right endpoint, f of bk is the left endpoint. And again, that's just because, well, G is this secant line between AK and BK. So G is going to be between the two endpoints. Okay. So either way, the squeeze theorem tells us that because, again, both f of bk and f of ak converge to f of x0, which is g of x0, the squeeze theorem tells us that g of xk is going to have to converge to g of x0. And that violates star, what we had way back. Right here. So the proof is finished. And to think the book wanted you to do this as a homework, you have to do all this as a homework in the book, which is pretty long homework. Okay, so now that we have this lemma here, we can prove Lucen's theorem. And Lucen's theorem is the following. Let's say we have f defined on a measurable set, and f is measurable. Then for any epsilon, there exists g and big F, both depending on epsilon, where g is continuous, g extends f, and E is almost F, or rather F is almost E, in the sense that if we excise F from E, the measure is going to be less than epsilon. And we will prove that in a separate video. All right. Thank you for watching this video, and hopefully this made sense, and hopefully this test run wasn't too bad. I apologize for the janitor interrupting me. I was just doing his job, obviously. And yeah, do let me know if you have any comments on this format, anything I can change, improve, etc., etc. And yeah, I'll prove Lucen's theorem in another video. All right. Have a good break, and Yeah, take care.